Despite the variety of games treated in general game playing, all games share a common abstract structure. Each game takes place in an environment with finitely many states, with one distinguished initial state and one or more terminal states. In addition, each game has a fixed finite number of players. Each player has finitely many possible actions in any given game state, and each state has an associated goal value for each player. The dynamic model for general games is synchronous update. All players move on all steps, although some moves could be no-ops. And the environment updates only in response to the moves taken by the players. Now, given this common structure, we can think of a game as a state graph, like the one shown here. In this case, we have a game with one player, with 8 states, named S1 through S8, with one initial state, namely S1, and with 2 terminal states, that's S4 and S8. The numbers associated with each state indicated the values of those states, and the arcs in the graph capture the transition function for the game. For example, if the game is in state S1, the player does action A, the game will move to state S2. If the player does action B, the game will move to state S5, and so forth. In the case of multiple players with simultaneous moves, the arcs become multi-arcs, with one arc for each combination of players' actions. Here's an example of a simultaneous move game with 2 players. If in state S1 both players perform action A, we follow the arc labeled A/A. If the first player does action B and the second player does action A, we follow the arc B/A. We also have different goals for the different players. For example, in state S4, player 1 gets 100 points, while player 2 gets 0 points. And in state S8, the situation is reversed. State graph captures the essential information about a game. And since all games that we're considering are finite, it's possible, at least in principle, to describe such games in the form of state graphs. Unfortunately, such explicit representations are not practical in all cases. Even though the numbers of states and actions are finite, these sets can be extremely large, and the corresponding graphs can be larger still. For example, in chess, there are thousands of possible moves in more than 10 to the 30th states. Fortunately, we can solve this problem exploiting regularities in the game to produce compact encodings. In practice, we rarely think of states as monolithic entities. More frequently, characterize states in terms of propositions that are true in those states. Similarly, we often think of actions as having some structure as well. This leads to a notion of a structured state machine like the one shown here. The overall structure is the same as in the simple state machine shown earlier, but in this case we've revealed the substructure of states. Now by itself this does not help us since the graph is the same size as before. However, actions frequently affect only some of the propositions that are true in states and leaves others unchanged. By exploiting these limitations on the effects of actions, we can encode state graphs compactly by writing logical rules in place of explicit graphs. GDL, or Game Description Language, is a formal language for encoding games in this way. As we'll see, it's based on symbolic logic. It's widely used in the literature and is used in virtually all general game playing competitions. Moreover, it forms the basis for some more expressive variants that have significant value in real-world applications, such as enterprise management and computational law. Here's an example of GDL, in this case the rules for the game of tic-tac-toe. Now we discuss the specifics of GDL in the next lesson. For now, the details are unimportant. The one thing to note is that this one page of rules fully describes a game with thousands of states. It's a significant savings over the state graph. The improvement in more complex games can be even more dramatic. For example, it's possible to describe the rules of chess with many more states in just about 4 pages of rules like these.